Go.
Hello, my name is Zane Steindler,
Hi, I'm Peter Hoang.
I'm Ryan Crane.
I'm Ezekiel Negron.
and we are Group 9. This is our 2023 fall semester FSE100 project called the Scorpion Killer. In suburban Arizona, scorpions are prevalent outdoors and have a reputation for inflicting harms to its victim. Our design project is a scorpion hunting robot that aims to eliminate scorpions surrounding the outdoor area. Scorpions are highly prevalent in desert climates, and they are lethal and deliver a deadly sting. The only viable methods of removing them requires intentional effort and care, like scorpion sprays, sticky traps, and pest control. Currently, there is no fully autonomous method of eliminating scorpions. Arizona is abundant in scorpions. Gilbert is rated the #1 most scorpion-prone city in Arizona, and Arizona is also home to the Arizona bark scorpion, the most dangerous scorpion in North America. Poison control centers in Arizona receive around 20,000 calls a year alone concerning scorpion stings. Our end users are the suburban Arizona residents, Arizona farmers, and anyone around the world with scorpion infestations. Other relevant people include people with bug infestations and investors.
Here are the customer interview summaries. The highlighted questions here are the most relevant questions that we took into consideration when making our product. Our customer feedback, they said that the concept was well thought out and the product did a decent job running on its own, but they did say that it was too expensive, too bulky, and did not support the weight of the circuitry. The solution, just to make a fully autonomous robot that can move on its own and seek out and kill scorpions in an efficient manner. Here are all of our designs. They're all pretty similar. 3 to 4 wheels, round base, and sensors. Our new design requirements needs to kill scorpions, be function automatically, structurally sound, and support all the weight of the circuitry.
Here is our first design in CAD. We have a 12-inch by 12-inch open box design with 4 wheels and a distance sensor and camera attached to the front wall. The open box design is there so a vacuum can fit in the box, but as you'll see in the next slide, we ultimately decided to scrap this idea for a more cost-efficient and safe method of scorpion removal in a mixture. And now, here is our actual design. We opted for, once again, a 12-inch by 12-inch box, but we decided to use a roof, so it would look more aesthetically pleasing. We opted for a design of 2 wheels and a swivel rather than 4 wheels in order to cut down costs. Rather than using a camera, we opted for the use of a photoresistor, which detects light, which is projected off of scorpions in the dark when a black light is shined on them. We also opted to use a mister rather than a vacuum, which will eliminate the concern of having to manually empty scorpions. Here is our circuitry. We have the Arduino, which provides 5 volts to the servo motor, the distance sensor and its pins, the photoresistor pin, and the motor driver pin. We have a 9-volt battery, which provides voltage to the L298N motor driver, which provides voltage to the gear motors. And all of our connections were made through a breadboard. Some changes were needed and made in our circuit design. First of all, we had 2 less gear motors, 1 less motor driver, 3 less batteries, and we swapped the camera for a photoresistor and also a vacuum for the mister, and all of those cut down on costs and weight. Here's a flowchart for our swap software design. First, the code checks if there's a light value of 20, which represents a scorpion being spotted in the dark with a black light on it. Servo motor will turn 45 degrees if it detects the light, which will turn on the mister, and then the servo will move back and turn the mister off. After that, well, not after that, but simultaneously, the distance sensor will detect if there's an object 10 inches in front of it, and if it does, then it will stop moving and turn left. And if it does not sense an object, it will move forward.
All right, so we have 4 slides of code. This right here is the void setup and the defining integers. Here we have the servo motor where it is defined and attached. The light is also defined, and all of the inputs and outputs for the hobby gear motors, distance sensor, photoresistor, and servo motor are defined. In code 2, we have the void loop, the if distance rule, and the if light rule. Essentially, what you're looking at the top of the slide is the trigger distance sensor and the distance value. So a distance is recorded consistently at the speed of light. If this distance sensor detects more than 20 inches ahead of the robot, it will move forward. Else, it will move backwards and then rotate approximately 45 degrees to the left. If the photoresistor records a bright value of over 20, it moves the servo forwards and backwards twice to trigger the mister on and then off for 2 seconds. Right here is the code for the move servo, turn off servo, move backward, and move forward function. And right here is the code for the turn right and turn left function.
Here is our demonstration video. As we can see, if there is no object in front of it, it moves forward, but it detected the leg of the table, so it moved backwards and turned left. Here we see the light being shined on a photoresistor, and this causes the servo motor to move and to turn on the mister. And here we see this happening simultaneously.
This is our augmented reality. As you can see, it is a simple representation of what a robot is supposed to do. We do have the dinosaur representing a scorpion, and as you can see, the robot went up to the scorpion and the dinosaur is eliminated. As for our materials list, we did use an Arduino with its wires, a photoresistor, a distance sensor, wheels and gear motors, servo motors, blacklight, and wooden pieces for the body. As you can see, the estimated cost of all these materials were around $58, and that is a 78% decrease from what our original prototype was at $269. The market cost, we do plan on selling our robot for $114.99. We took into account our raw materials cost, which is around $58, and our miscellaneous expenses, which we calculate to around $5, and our labor, which is $20, which is total around $83. But we do want to profit from our robot, so we did add an extra $30 on top of that price, and that's how we got our $114.99. For our work, or how we divided our work, we did collaborate on every part of the project, but we did list the main things that each person took charge on. Comparing the competition, there's always scorpion sprays and powders, manual labor, and expensive pest control companies. Why you should invest in our robot is because it is the only one out there that kills scorpions. It is valuable anywhere, not just Arizona, and just anywhere with scorpions. And it is a long-term investment. You buy it once and you don't have to buy it again. What we learned is the importance of engineering design process and the importance of time management. We also learned that it is especially super good to ask for help when you need it or when you're stuck. And something that we would do differently if we ever did this project over again is using a Gantt chart to specifically lay out what we need to do and how we would split the task. What we would also do is ensure that we have more time just for any problems to come up and we are able to fix them.
So here's our summary. The Scorpion Killer is a Roomba that hunts down scorpions at night with a mister, and you won't ever have to go outside in fear of being stung by a scorpion ever again. No need to be using your sprays all over trying to kill them scorpions when you have a robot to do it for you. You get that peace of mind, and you won't end up in the hospital like that guy. Here's our references and citations. Thank you for your time.